Public key encryption protocol, known as asymmetric or two-key encryption, uses different keys for encryption and decryption based on mathematical functions rather than substitutions or permutations. Two protocols are focused in this chapter are Reverse-Shamir-Edelman protocol or RSA algorithm, Diffie-Hellman key exchange protocol. Computationally infeasible to determine the decryption key given the algorithm and the encryption key. For example, if A wishes to send a message to B, A encrypts the message by using B's public key. On receiving the message, B decrypts it with the private key. RSA algorithm has three phases: key generation, encryption, and decryption. The key length is typically 512 bits, which requires enormous computational power. So it is very difficult to find out the decryption key by the hacker. So the key generation algorithm phase. So first choose two large prime numbers, say P and Q. Calculate the value n, P into Q. Calculate Euler's torsion function phi of n equal to P minus 1 into Q minus 1. Choose the value of E such that E is relatively co-prime to phi of n, that is the GCD value of E and phi of n must be equal to 1. Now calculate the decryption key D such that E into D mod phi of n should be equal to 1. Now the public key is a pair of E and n and private key is a pair of D and n. The encryption can be done as the ciphertext C is equal to P to the power E mod n, where P is the plain text, and the decryption is can be done as C to the power D mod n, so where P will give back the plain text. Example for RSA algorithm implementation, we need to choose two large prime numbers. For the simplicity and for understanding, we are taking a very small prime numbers as P equal to 3 and Q equal to 1. Calculate the value of n, P into Q. Calculate Euler's torsion function, P, which is P minus 1 into Q minus 1, so it becomes 20. We need to choose the value of E such that E should be relatively co-prime to phi of n, that is the GCD must be equal to 1 and the value of E should be greater than 1 and it should be less than phi of n. So you need to take a value of E within that range, so any prime numbers. So in this example we are taking the value of E as 3, we can take the next prime number as 5 or 7, but the prime number should be within the range 1 to phi of n, greater than 1 and less than phi of n. So and we need to calculate the value of D such that E into D and mod of phi of n should be equal to 1. So this is just a trial and error method. So we start with all the prime numbers. So let's take the prime number as 3, then 3 into 3 mod 20. So that the remainder is not equal to 1, so we will take the next prime number, so 21 mod 20. So we get the remainder as 1. Let's take the value of 7 as the value for D. Now the public key is 3 and 33 and the private key is the 7 and 33, that is E and N value, D and N value. Let's calculate the ciphertext. For this example, we are considering the plain text as 1001. The binary value, its decimal equivalent is 9. So 9 to the power 3 mod 33. The remainder is 3. 3 will be transmitted over the communication channel. At the receiver end, the receiver will decrypt using his public key. So the decryption process is the ciphertext to the power D mod n. So we get the plain text value back. So that is the value 9. So this is a textbook problem you need to solve. Here the initial prime numbers P and Q is given, and the value of E is also given. So you need to find out the value of then you need to find out the Euler's quotient, and you need to find out the private key D, and you need to encrypt this message, and you need to decrypt the message also. So try to solve this problem. Diffie-Hellman key exchange protocol. Diffie-Hellman key exchange is a method of securely exchanging cryptographic keys over the public channel. As we know, the sender will be using a key for the encryption process. Now, how to send a key to the sender? Because when the key is sent as it is, it might be hacked by the hacker. So we need to securely transmit the key to the sender as well as the receiver. So this Diffie-Hellman key is used for encrypting these keys, encrypting the sender key as well as the receiver key. Then the keys are exchanged. So used to exchange a secret key between the two users, that is for sender as well as to the receiver. So for encryption of the keys, we use the asymmetric encryption. So sender key is encrypted using a different key, as well as receiver key is encrypted using the using a different key. And shared secret key will be generated by both the sender and the receiver. So this shared secret key is the common key. So this key will be later used for the symmetric encryption. So the shared secret key will be used to encrypt the communication process. Let's see the Diffie-Hellman algorithm. Assume the public key is available. This will be known to both the sender and the receiver. If you consider Alice as a sender and Bob as a receiver, now the Alice will select the private key A, and the Bob will select the private key as B. Now they generate the key, so which is nothing but P to the power A and mod G, and Bob will also generate the key Y. It should be Y here. P to the power B mod P. So now the exchange of the generated keys takes place. So Alice will receive the key Y, and Bob will receive the key X. So now they will generate a key from this. They will generate a secret key. So this secret key will be used for the communication. For the encryption and decryption, they are going to use this key. So this key is generated as received key, that is Y to the power A mod G and Y to the power B mod B. So A and B is private to the sender and the receiver, whereas the P and G are the public keys which will be known to both the sender and the receiver. So and the Ka value will be equal to Kb. So now you will have a symmetric key. Symmetric key encryption means the same key is used for the encryption as well as for the decryption. So finally in the Diffie algorithm, you get a symmetric key for the encryption and for the decryption. Let's take a simple example to understand the Diffie-Hellman algorithm. So let's say the Alice and Bob, they get the public numbers as P equal to 5 and G equal to 7, and there is a condition that P should be the primitive root of G. Now what do you mean by the primitive root of G? So if we have to say a certain number is a primitive root of another number, then it should satisfy this condition. Now let's say 5 to the power 1 and mod 7. So the remainder is 5. Similarly, we will calculate 5 to the power 2 mod 7. Then the remainder what we get is 4. 5 to the power 3 mod 7. So the remainder is 6. 5 to the power 4 mod 7. Remainder is 2. 5 to the power 5 mod 7 equal to 3, and 5 to the power 6 mod 7 is equal to 1. So we need to repeat the steps till we have let's write it as p to the power from a mod g. Okay, the value of a should be from 1 to g minus 1, and we should be able to get the remainders as, or the remainder should be all the numbers between 1 to 6. So we have the remainder. It need not be in this order, it can be in any order, but if you see the remainder, it covers the numbers between the range 1 to 6. Then we can say p is the primitive root of g. So we can have 1 over here, or we can have 3 over here, doesn't matter, but it should have the numbers in the range 1 to 6. So then only we can say it is a primitive root of a number. So usually in the exams they do give these values, and let's say the Alice has selected the private key value as 3 and the Bob has selected the private key as 4. So these values will be known only to the sender and for the receiver. That's why it is termed as the private key. Now they compute the public values. So they compute x as 5 to the power 3, that is p to the power a mod g. So we get the value as 6. Next p to the power b mod g. So the remainder is 2. Now these two keys are exchanged. So Alice and Bob will exchange their public numbers. So Alice will receive the key from Bob, and Bob will receive the key from Alice. Now they will compute their symmetric keys. So this is the key which they are going to use it for their encryption, and the receiver will be using the same key for the decryption. So your both encryption and the decryption key, that is the secret key, can be calculated as y to the power a. So using the private key they will compute. So now the shared key is 1. So this key is used for the encryption purpose as well as for the decryption. Authentication techniques are used to verify identity, verifies the authenticity of both the message and the message sender. Message content is authenticated through the implementation of a hash function and encryption of the resulting message digest. The sender's authenticity can be implemented by the use of a digital signature. Hash function produces a hash value, also called as fingerprint of the message, as fingerprint is unique to everyone, and this hash value is added at the end of the message before transmission. The receiver computes the hash value from the received message and compares it to the received hash value. If the two hash values are the same, the message was not altered during the transmission. Hash function takes the message as the input and it computes the message digest or the hash value. Hash function has the following property. The authentication algorithm is not reversible, that is, given a message digest, that is the hash value, it is computationally infeasible to find the original message M. And it is computationally infeasible to find two different messages M1 and M2 such that their hash values are equal. As I said earlier also, hash value is just like a fingerprint. It is unique for the different messages. Message authentication can be implemented by two methods. One is combining the hash value with the encryption, that is after the hash value is generated, it is encrypted and then transmitted. And second implementation wherein the hash value is not encrypted, the computed hash value is attached with the message and it is transmitted. Two types of implementation of message authentication is shown in this block diagram. You can see in the block diagram, user 1 message, the hash value is computed, then the computed hash value is encrypted and it is attached with the message and it is transmitted. At the receiver end, the message and the hash value is separated, the hash value is decrypted and the computed value of the hash is compared with the hash value attached with the message. If they are equal, then the message is sent to the application level of the user or to the application of the user. This is the second method wherein the hash value is not encrypted. User 1 message generated, hash value is computed, the computed hash value is sent along with the message. At the receiver, the message and the hash value is separated. The message hash value is computed again to check whether the message is altered or not. So it is compared. If they are equal, then the message is forwarded to the user. We are going to discuss secure hash algorithm, which is one of the authentication algorithm. In brief, it is proposed as a part of the digital signature standard. There are many variants of SHA algorithm. We are going to discuss SHA-1, which takes a message with maximum length of 2 to the power 24 and produces a 160-bit digest. That is, the hash value is of 160 bit in length. SHA-1 uses 5 registers R1 to R5 to maintain a state of 20 bytes. 20 bytes are nothing but a 160 bit. So the steps are as follows. So the message will be divided into 448 bit sized blocks. Next, we need to pair the message. So if message block is considered as YAM, then the number of bits to be padded is LM. So which is nothing but 448 module 512. So the remainder will be 64. That means 64 bits will be padded to the 448 bit sized blocks. Next, each block must be expanded. So from 512 bits, that is 16 words, each word is 32 bit, or we can say 4 byte. Now this 512 bit, that is 16 words, should be expanded to 80 words. Let's label the 16 words as M0 to M15. Now we need to calculate the 80 words. So the first 16 words will be the message word itself. So we can see in the equation Wi equal to Mi. So I value will be from 0 to 15. Next, the remaining words, we need to have up to 80 words. That is, from 16 onwards, the words are computed in this fashion. So here we have this symbol which means the left rotation by j bits. Here the left rotation by 1 bit. Step 3, bits from each incoming block of W. We have 80 word blocks are mixed into the state in 4 stages. Each stage has 20 rounds, so we have totally 80 rounds. We can say we can of the in 4 stages. I value is 0 to 79, representing 80 rounds in the 4 stages. So delta value is computed by left shifting 5 times. Then we are using the function f, which we are going to discuss in the next slide, and the ri, then r5 plus wi is the word of that round. It can be 0, 1 based on the value of I, and ci is the constant value. Next we assign the r4 to r5, r3 to r4, r2 to r3, r1 to r2, and delta is assigned to r1. So the message digest or the hash value is produced by the concatenation of the values of R1 to R5. As we know, there are 8 iterations. The diagram represents one of the iterations. Here A, B, C are nothing but they represent R1, R2, R3 and R4 and R5. So first we calculate the delta, right, which is nothing but the left rotation of R1 by 5 bits. Next we use a function f, which takes the input as R2, R3 and R4. Next we add it with the R5. So we can see here the output of Fi is added with R5, and the output of the left rotation of R1 by 5 bits is also added. Next we are adding with the Wi, the word at ith iteration, and the constant value ci at ith iteration. Next we do have some assignment statement. R4 is assigned to R5, so we can see here D, which represents R4 is assigned to R5. Similarly, R3 value is assigned to R4, so we can see here, and R2 with the shifted with the 30 bits, that is not shown here directly, they have shown with the R2 value to R3. Next R1 value is assigned to R2. Next the delta value, that is the addition of everything, is assigned to R1. So this is your f function. So suppose if f function takes ABC, then if the iteration lies between 0 to 19, then this is the evaluation way. If it is between 0 to 39, then this is the evaluation of f. Or if the I values varies between 40 to 59, then this is the evaluation. Then the I value between 60 to 79, this is the iteration. This is the SHA algorithm in brief. We have not discussed much in detail, so whatever is specified in the textbook I have tried to cover in this lecture. A digital signature is a mathematical technique used to validate the authenticity, that is the user is the genuine user or not, and integrity of a message, a software or digital content. It's like a handwritten signature or stamp seal, we can say, and it is intended to solve the problem of the tampering and impersonation in the digital communication. It is based on asymmetric key cryptography, but it is not meant for ensuring the confidentiality of the message. And they are also called as electronic fingerprints because the signatures are unique. The digital signature will securely associate a signer with the document in the recorded transaction, and they use a standard accepted format called public key infrastructure. It is a technology for authenticating users and devices in the digital world. For example, to understand this digital signature, let us take an example. Jane signs an agreement to sell a timeshare using her private key. The buyer receives the document. The buyer who received the document also receives a copy of Jane's public key. If the public key cannot decrypt the signature, it means the signature is not Jane's or has been changed since it was signed. So then the signature is considered to be invalid. So basically here the sender is going to generate the keys. He is going to generate the hash value of the message. Then the hash value will be encrypted by using one of his private key. Then it is sent to the receiver. Receiver will be receiving the message and the encrypted hash value and also the public key of the sender. Suppose the receiver is not able to decrypt the message using hash value using the public key. That means the message has been altered. This block diagram shows the digital signature process. We have the data here. Using the hash algorithm, the hash value of the data is generated. The hash value is encrypted by the private key of the signer or the sender. Now the message or the data along with the encrypted hash value, we can call it as a digitally signed document, is transmitted over the network. At the receiver end or at the verifier end, the digitally signed document will arrive, and the hash algorithm is applied on the data part, so which generates the hash value, and also the document has the encrypted hash value which has to be decrypted by using the public key of the verifier. So if the verifier is able to decrypt, that means the data document is not altered, or it also says that the data document is from the genuine user. So to verify or to detect whether it is altered or not, or it is from the genuine user, the hash value will be compared. The hash value from the hash algorithm and the decrypted hash value will be compared. So if they are equal, then it is considered as the signature is valid. So even the algorithm, RSA algorithm, can also be used for the digital signature. As well know, RSA algorithm is an encryption algorithm. So basically the encryption, if I say the encryption process, it is to maintain the confidentiality of the data so that the hacker should not be able to understand what data it is. So in the encryption process, what we do is using the public key of the sender, the data will be encrypted and it is transmitted. At the receiver side, the receiver will be using his private key to decrypt it. But in the case of digital signature, the procedure is slightly different. When RSA is applied, the message is encrypted with the sender's private key. So if you're comparing this RSA implementation with this block diagram, here the entire message is encrypted and this entire message itself serves as the digital signature. And at the receiver side, the receiver is going to decrypt using the public key. So the entire message is encrypted with the sender's private key and it is sent. And at the receiver side, the receiver should be able to decrypt it using the public key. So if the receiver is able to decrypt, that means the packet or the data has come from the authentic user.